Electric fields come from charges, but where do magnetic fields come from? What's inside a magnet that generates a magnetic field? Well, let's find out. Let's start with something that we already know. We know that a current carrying loop generates its own magnetic field. And if you draw the field lines, you will see that these field lines resemble that of a bar magnet. In other words, we can say a current loop behaves like a tiny magnet. And it doesn't matter what that shape of the loop is. It doesn't have to be circular. As long as it's small enough, or as long as you go far away from it, that current loop looks very small to you, then the magnetic field lines will resemble that of a tiny magnet. And so we can go ahead and now say that a current loop behaves like a tiny magnet. But guess what? Tiny magnet is not a very technical term. So you know how we say it technically? We say a current loop behaves like a magnetic dipole. That's the technical term for it, but it's the same thing. Okay? And it also feels good to say that. Go ahead, say it. Current loop behaves like a magnetic dipole. Wow, feels good, right? Anyways, this is great news because now if you want to use magnets in any experiment, we don't need actual magnets. We can get rid of them because we can use current loops. And the advantage of a current loop is that you can control the strength of that tiny magnet. For example, if you increase the current, and the advantage of this is that you can control the strength of the magnet. If you make the current stronger, you get a stronger magnetic dipole. If you make the current weaker, you get a weaker magnetic dipole. So you can alter that strength. And so that brings us to the next question. What determines the strength of this tiny magnet or the magnetic dipole? I mean, current is definitely one of the things, but what else determines the strength of this dipole? And again, there's a technical term for it. So we're talking about strength of this magnet. And the technical term for the strength is, we call it moment. So technically you would ask, what determines the magnetic dipole moment? Okay? And the symbol we use is M. And clearly, current is one of them. So the magnetic moment is proportional to current. But what else is it? What else determines the magnetic moment? Well, what about the number of loops that you use in your coil? If you double the number of loops, then you will have twice as much magnetic moment, right? It's as if you have it's as if you have 2 loops, and so it'll be double. If you have n loops, then it'll be n times more. So the magnetic moment is also proportional to the number of turns that you have. And it also turns out that the magnetic moment is proportional to the area of this loop. It doesn't matter what shape it is. It can be circular, square, rectangular, but the area is what matters. And so the area also determines the magnetic moment. And if you're wondering, like, how do we know that this is it? Like, how do we know exactly this is the relationship? We will derive this in a future video. But as of now, intuitively, hopefully this makes sense. And so that's how you calculate. This is how we like to calculate the magnetic moment or the strength of this tiny magnet. It's the number of loops multiplied by the current multiplied by the area. So given this, we can now look at the units of our magnetic moment. Can you quickly pause the video and write down the units of this? Go ahead, give it a shot. All right, N has no units, it's a number. I is amperes, and area is meters squared. And so we represent the moment in ampere meter square. So if somebody asks you, how strong is your magnet, this current loop, how strong is it behaving like a magnet? You say, so many ampere meter squares. That's how we represent the dipole moment. Okay, here's a question for you. Do you think dipole moment should be a scalar quantity or a vector quantity? What do you think? Well, the magnetic fields certainly depend upon the orientation of a magnet. And similarly, it will depend upon the orientation and the direction of the current, right? So it makes sense to think of dipole moment as a vector quantity. So now we need to ask ourselves, how do we define the direction of the dipole moment? Well, look over here. Over here, the magnetic field is produced upwards. At least on the axis, you can sort of see the magnetic field is upwards. So over here, we could say that the direction of that dipole moment is upwards. But how do you represent this in general? How do we represent this in general? Well, if you think in terms of a magnet, if you imagine that this was a magnet, then you could say that the magnetic dipole moment is from south pole to north pole, as you can see, because the field lines inside the magnet run from south pole to north pole. So that's one way in which we can represent that. But let's forget about that hypothetical magnet. If I were to just look at this loop and from there, define the direction of the moment, how would I do that? Well, this is where we can bring in our famous, this is quite famous now, right-hand thumb rule. You can see if you clasp your right hand in such a way that the four fingers represent the direction of the current, then notice the thumb is showing the direction of the magnetic moment. And so we can use our right-hand thumb rule to tell you the direction of the magnetic moment. So let me take another example. Let's see if you can use your right-hand thumb rule to tell the direction. Let's say we had a current carrying loop this way, so that the current is flowing in this direction. Can you pause the video and use your right hand and tell me what direction would be the magnetic moment in this case? All right, you would have to use your right hand, clasp it such that the four fingers run in this plane, in this direction. If I were to do that, it would look somewhat like this. Notice the four fingers are going in the direction of the current, and the thumb is pointing inwards. So in this case, we would say the magnetic moment is pointing into the screen. So magnetic moment is a vector quantity. All right, the last question I have, which could be probably the most important questions about dipoles, is what's the difference between a magnetic dipole and an electric dipole? Remember electric dipoles? Electric dipoles were two charges, one positive and one negative, equal magnitude, separated by some distance. We call them the electric dipole. And if you look at the field, electric field produced by that, notice it is so similar to our magnetic dipole field. Just to jog your memory, for electric dipoles also we defined a moment, the strength of that dipole. We said that the electric dipole moment, which was given by P, the symbol we used was P, we said equals the charge, the magnitude of the charge, which is the same, times the distance between these two charges. This is how we defined our electric dipole moment. And again, the way we looked at the direction of the electric dipole moment, over here we see, again, the dipole is sort of pointing upwards from negative to positive charge. That's how we defined it over here, okay? Now, the big question that I want to ask you is what difference conceptually do you see between magnetic dipoles and electric dipoles? What is the major difference that you might be seeing? Of course, you might say formula is different, units might be different, but conceptually the major difference that I see, it's important, is when it comes to electric dipoles, they are formed by putting one positive charge and one negative charge together. We can call them monopoles because monopoles. So two monopoles, when you keep them together, that's how we get electric dipoles. But for magnetism, notice, we don't have monopoles. In magnetic fields, we only have dipoles. Big difference. And so it's for that reason you can see that electric fields start from one monopole, end into the other monopole, start from positive and end into negative, always. But for magnetism, we don't have monopoles, we only have dipoles. And therefore you notice that they will always be, they don't start from anywhere, they won't end into anywhere, they will always form closed loops. In magnetism, we only have dipoles, no monopoles. At this point, you might say, okay, but what about inside a magnet? Magnets definitely have north and south, so they do have monopoles, right? No. Even inside magnets, the magnetic field is generated by current loops. Now you might say, hey, where are there current loops inside a magnet? Well, remember, everything has atoms, and atoms are basically, you can think of them as electrons zipping around positive charges. Now, electron is a charged particle, and as it moves, we get a current. And so the very fact that the electron is going around gives us a current loop, which generates a magnetic dipole. So notice, even a single atom behaves like a magnetic dipole. And it turns out that the electrons have a tendency to spin around its own axis. Now, of course, in reality, the word spin, at least for electrons, means a very different thing. But we don't have to worry too much about the details. As of now, we can just imagine the electrons are spinning around its own axis. And when they do, we again have a current loop. Because electron is a charge, we can sort of have a current loop over there. And that means a single electron itself behaves like a tiny magnetic dipole. So notice that every single electron or atoms, they all tend to behave like magnetic dipoles. There are no monopoles anywhere. And now, if this is making you wonder somewhere in the back of your head, but wait a second, everything has atoms and electrons inside of it, so shouldn't everything be magnets? Then you're on the right track. The next step, of course, would be to dig into the atoms and think about what really happens at the atomic level and when the atoms come together to form objects. But of course, that's a story for another day. But the point that I wanted to drive home over here is that everything when it comes to magnetic is dipoles. We don't have magnetic monopoles. So long story short, current carrying loops behave like tiny magnets. We call them dipoles. And the strength of that tiny magnet, which we call magnetic dipole strength, is given by the product of the number of loops times the current times the area.